Welcome, everybody. My name is John McDonnell, and I'm super excited here to be joined by the co-founders of Generally Intelligent. Here, we're having this forum here at South Park Commons. South Park Commons is a home for technologists, builders, and domain experts figuring out what's next. Our community programming includes forums, builder squads, and inspiring guest speaker events like this one. If you want to learn more or are interested in applying, go to southparkcommons.com. So Generally Intelligent, I'm going to make sure I get this right, is working to unlock human creativity and insight by developing general purpose agents with human-like intelligence that can be safely deployed in the real world. And so here today, we welcome Generally Intelligent's co-founders, alumni of SPCE, Kanjun Qiu and Josh Albrecht. Welcome so much to the show.
Thank you. Yeah, we actually were in the first cohort of SPC in 2016 with a different company.
Yeah. So for the audience, why does Generally Intelligent exist?
So we're very interested in building agents that can do things safely in the world. And I think, today, as humans, we do a lot of craft work that we really don't want to do. But technology historically has taken away a lot of that craft work and opened up entirely new entirely new worlds for us to be able to do completely new things. And we think that AI systems, generative ones today, but in particular systems that can assist us by doing things in the world, will open up incredible, extraordinary frontiers. And that's what we're really excited about.
So there are multiple research foundations working on AI. What is it that you do differently?
Our focus really is on making generally capable agents. That's why, Generally Intelligent, what we really want is to focus on systems that do stuff in the world. We're not focused on robotics. When we say the world, we usually mean in more like a virtual setting or in a digital setting. But if you ask a chat model to go buy you groceries, maybe it'll say yes, or oh, I did that, or okay, what kind of groceries would you like? But it's not going to buy you any groceries, right? We're still a long ways away from agents that we would trust to actually do things on our behalf. And a lot of what we need to do to get there is figure out how to make them safe and understandable and inspectable and explainable so that you would actually trust it to do that, trust it with your credit card information, trust that it won't delete all the files off your computer, make something that can act on your behalf in a way that's reasonable and safe and capable.
Yeah. And that might be a long way off. If you look back at your work, say in 5 years, how will you know if you've succeeded?
Yeah, I think 5 years from now, I think a lot of things will be different.
Yeah.
So it's very plausible that this vision will be accomplished. But I think in 5 years, what I want is for people to feel very different about the way that they interact with their computers. I think we're at the beginning of what feels like a computer revolution or Xerox PARC-like revolution, and we don't think that it's that far away. It's going to delete my files today, but I think for us, and this is why our approach is very focused on what problems are the right problems to solve, and how do we build these systems in a way where they're fully interpretable, understandable, and modifiable by the user, because trust, I think, is basically the core problem of this. Is the core problem.
Yeah. So how do we get there? How do we build this world?
That's a good question. There's a lot of work to be done. We have research in a number of different veins, basically. One of them is about figuring out what are the right problems to tackle, what are the right questions to ask. So we actually spend a lot of time figuring out what even should we be trying to do? Instead of just optimizing some random metric like ImageNet score, okay, is that really the right thing to be doing? So in that vein of work of figuring out what the right problem to ask is, one thing that we worked on recently was Avalon, which is a reinforcement learning simulator, where we have agents that can do a wide variety of things in this simulated world. So that gives us a place to explore a huge world. They can be up to a kilometer squared. These are much more complicated worlds than, say, Atari. There's a reason for curiosity and exploration and those sorts of things that in Atari, and other limited reinforcement learning settings maybe didn't make as much sense.
Right. We're really interested in settings in terms of problem selection where if the agent does have human-like attributes like curiosity, or really if the agent's really good at planning, we're going to be able to tell based on this problem setting. Like right now, in a lot of the problems that are being solved today, you just can't tell even if it's better.
Yeah, so that's one place, is kind of the problem selection, and then creating tools is another thing. So Avalon itself is a simulator. It's a thing that we open sourced and released to the research community. But we're also interested in other tools that are helpful for making more capable systems. So we released some things around like an editor, and we're working on some stuff related to just making it easier to run experiments. We have our own sort of infrastructure that we use, which we would like to open source someday, that kind of abstracts across cloud providers. We're really about like building tools and making it easier to run experiments and easier to run more robust experiments. So tuning your hyperparameters properly, that sort of stuff. And then I'd say a third
we would love to talk about this category more, because it's actually really exciting, but we have papers under submission right now. And they're anonymous, so we're not allowed to talk about it.
And maybe a final thing that I'll talk about a little bit is we do a little bit of theory work as well, trying to understand, a lot of people I think don't realize that like nobody knows still why deep learning works exactly. Like, Siri recognizing your voice from your phone, like literally no one can tell you exactly why it works. We can tell you all the matrix multiplies, but we don't have good like mathematical theory that tells us like why exactly did it learn those features as opposed to these other features, and why does it work so well? We don't have, there's still a lot of unanswered questions. So we're really, really interested in these sort of fundamental questions of learning, and also especially how those apply to agents. So again, we have some other work under submission that we're working on there. We can't quite talk about, but like that's another kind of vein of things that we work on.
Yeah, one interesting thing in that vein is kind of an analogy, which is in other areas, we build safe systems because we understand how they work. So with nuclear power plants or with airplanes, we like fully understand how both of those things work, and that's how we end up with really, really safe, predictable, reliable, robust systems. And here, we're evolving these systems, and so there's a lot of unknowns, and as long as we're just like purely evolving these systems and we can't get good guarantees about what they're going to be able to do, we think that's not a good state for the world to be in.
Yeah, I mean, I guess what does it mean to understand, right? I mean, like there's different, as you pointed out, like, okay, you can look at the matrix multiplies. Like, what are the kinds of insights that could really improve, like, say, safety?
Yeah, so we actually do have a paper on safety that we had at NeurIPS in December, so last month at the AI safety workshop, that goes a little bit towards this. So one of the things that we worked on was looking at the ethics data set. So one part of this data set is the common sense part, which is like, okay, here's a scenario, is this right or wrong? So I drove over my neighbor's driveway. Seems fine. I drove over my neighbor's dog. Not fine, right? So can you get people to say like, oh yes, this is right, this is wrong, and can you get AI systems to say this is right or this is wrong? And what we showed is that by prompting, large language models in a particular way, you actually can get them to have higher than average human performance on this, right? Which is kind of strange if you think about it. You're like, wait, should I really just be asking like, this other random large language model, like if this is right or wrong? And the answer is no. If you really look into the errors, you see that the kinds of mistakes that they make are very different than the kinds of mistakes that people make. So we also had people explain their reasoning, and we realized that a lot of the mistakes that people make are like they clicked on the wrong button. They meant to say right and they just clicked on wrong, but their explanation was correct, right? Yeah. Or there's like a cultural reason, or there's like they had a very legitimate reason for describing like why this was wrong. And you're like, I hadn't thought about that before. That's like a good point. Yeah. Whereas the models did not have that at all. The models were really anchored on like the words that happened. Yeah. So if you say like, I poured the coffee into the cup, or I poured the burning hot coffee into the cup. One of these it thinks is like fine, and the other one's wrong. But like, yes, coffee is hot. That's fine. That's just how it is. It's not wrong. It's just it latching on. Like burning hot sounds bad. Like that's usually correlated with bad things. And so really, these kind of measures reflect more on what types of questions we're asking as people than they do about the system's capabilities. So I think one of the things that we need to do is like probe more adversarially and look at like in an actual deployment, in a real like worst case scenario, how do these things work? I think there's lots of things that you can do. We also looked at this in Avalon, looking at like where do the agents fail, et cetera. So I think it's a practical question of like, how do you look at the places where things can go wrong and like keep fixing those and keep understanding those? And also like, with large language models, realizing that they're really latching onto these like features of words and patterns in words, and they're not necessarily doing reasoning in the same way as us. And if we really wanted to make something that was robust, that we would trust to do ethical systems, we might want to put in a little bit more of like how we do ethical reasoning or train it in a slightly different way.
And then I think this is kind of one lens on it, which is to take a model that's already been trained and kind of like poke at it in different ways. There are a couple other lenses that we look at in terms of understanding as well. So Avalon, we mentioned briefly, is a 3D reinforcement learning environment in which you are training agents that are trying to eat food and survive. And it's a reinforcement learning setting, and it maps directly onto the VR action space, which means that anything you do in VR, you can put into the space for an agent to do. That just like really increases diversity. And the reason we built Avalon ourselves is because we're really interested in problems where you can incrementally increase the difficulty of the problem and use that to probe where the systems are failing. So here in Avalon, you can do something like test-driven development, where you can have a whole suite of problems and you can run the agent and be like, okay, I've trained the agent, I've run it, and it's working on this suite. Now you make one problem a little bit harder. Maybe you make the climb wall taller, and now it fails. And you're like, that's interesting. Like, why is it failing in this case but not in this case? And so an environment that's like fully controllable like this is another way of probing at agent behavior and capability. And then there's yet another way of probing at neural networks, which is kind of from the theory perspective. So we do a fair amount of work on theory and kind of like pragmatic engineering theory. One example of published work in this vein is there's like some work on neurotangent kernels, the NTK, which is more of a toy setting. And then there's also some work that's pretty interesting on questions like, I think there was some recent work on for models, you can prune most of the data that you're giving them and still get the same performance and the same results. So some of that data is doing a lot more in terms of what the model is learning than others of the data. That's like an example of a type of thing that would lead to better understanding of what's going on.
Yeah. I mean, something I'm really struck by some of these examples. So for example, the burning hot thing, to even think to probe that is kind of a clever thing, right? And so I'm kind of curious, it's like, are we gonna have to get really good at figuring out like super great probes?
Well, that particular one actually came from my background because I did natural language processing research and machine learning research like before we had neural networks. And there we only had n-grams. Like we only had very simple statistical models of language. And my hypothesis was like, well, I wonder if they sort of work the same way. And they do kind of work the same way. So that's kind of what inspired that. But I think that goes back to the like question of if you really understand how these things work, then it's easy, like it's much easier to make up these kind of examples. So I think, maybe a thing for everyone in the audience and everyone listening is like, I think one thing I'd put out there is I do think it's really worth understanding deeply how these things work. Like there's a lot of really good classes and materials that like go way into the depths, and it's not as complicated as it seems. Like it might, take an extra month or two, but I think it's really worth learning the fundamentals because it'll give you a much better intuition for like where is this going to work and where is this not going to work. So yeah, hopefully we can get some more people to help come up with these examples and break things. And I do think it'd be nice to see more of a culture of like builder breaker, like in the same way that we have in computer security.
Yeah, do you wish that there was as many people like jumping into like safety stuff as there are jumping into like, I don't know, building startups off of OpenAI or something?
We have seen we have seen a lot more people going into safety, so that's great. Yeah. And we do see some people that are trying to break these systems too. Like I think Riley Goodside and our friend Simon, they showed this like prompt injection thing. It's like, oh, okay, that's like a way of breaking things. So people are trying to break them, and I think that's good. I think we should be constantly doing that.
I also think startups trying to use it is a good way of trying to break it. Right. Yeah. So that's like a very pragmatic way of trying to break things.
But it's amazing how much red teaming happened for free when ChatGPT launched, right?
Exactly. Yeah. The world is a good red team.
Yeah. I was curious about Avalon, and I think that you've kind of alluded to part of this, but I feel like there's so many different kinds of environments that you could try to reinforcement learn in. And so you guys kind of put a stake in the ground and said, okay, we think this is the really useful environment to try. What are some of the things that you consider when choosing that?
Well, I think I would first say that Avalon is like one example of an environment. We're not necessarily tied to only working in Avalon.
Of course,
it's like an example of one. But part of the reason that we made it is that it is an environment in which we can express many different tasks with the exact same like setup.
We should have a nice video of it. I wish that it were running so you know what we're talking about.
Yeah,
but if you go to our website, generallyintelligent.com, there's a big video. You can look at Avalon. It's like a colorful, 3D environment.
Yeah. But one of the main things that we were thinking about there is like we wanted a place where all of the tasks were sort of in the same world. You could do multiple tasks during the same lifetime or transition from one to another. You could learn things that transferred from one to another. Previous work like Atari or like a meta world, in an Atari game, if you learn a lot about Pong, it doesn't help you at all in Montezuma's Revenge. Like those two things do not transfer at all, really. Whereas in Avalon, if you learn about like walking, it really helps you to learn about some of the later tasks. If you learn about eating, it really helps you learn about jumping and climbing. Like these things are part of the later tasks, and there's more of a smooth on-ramp. It's kind of, in the same way that a lot of these other models, as you train them on lots of real-world data, they kind of get to see lots and lots of different edge cases. That's sort of what we need for reinforcement learning, is like lots and lots of different problems that are all in the same space. And so this was an attempt to start at least moving in that direction, so we can have a little bit more diversity that the agent can learn over this like broader distribution of tasks.
Yeah, and the things we considered using Minecraft. We would love to use it, but it's so slow.
Yeah.
And so Avalon is about 100 times faster than Minecraft, which means that if you're training an agent, you can train it 100 times faster. So that's a lot. Yeah, for us, it's really important.
Yeah, just like run my test suite. Like, okay, that's
Yeah, exactly.
Yeah,
Runs
especially
immediately.
if you want to have lots and lots of tasks, one of the things you get into is like, well, if we're going to evaluate it on 1,000 tasks and each task takes 10 minutes to evaluate, oh, wait, like it starts to get actually really slow to evaluate. And we wanted this to be accessible to the academic community. So we wanted to make sure it was something where the baselines could train really quickly, you could evaluate the task really quickly. As we start to move into other more realistic settings, like that might not necessarily be accessible in the academic setting.
Yeah. Was it important? So one aspect that it has is you have an agent that's embodied, at least kind of. Was that an important part of the decision as well? Or?
Yeah, it was. Yeah, it was very helpful to have an agent that is embodied. So it's kind of this agent that's like walking around in like a 3D world, and it's very helpful to have that just because it's easy to think about. Like, when I am embodied, like what is a rat capable of, or what is a dog capable of? I would say like our current suite of Avalon tasks that we have public are like a rat or dog intelligence. And it's useful to be able to think about questions of planning or exploration in that framing because it's such a natural framing to me as a human. Whereas if I'm thinking in like language space, it's like, okay, or in 2D image space, it's like, okay, how do I know if this is a thing that a dog would be able to do? Like, I'm not really sure. So that's one thing. Second thing is, in reinforcement learning, we talk to a lot of researchers. We have a podcast where we talk to lots of researchers. And the biggest thing we heard from other researchers is that the biggest bottleneck holding the field back is lack of good environments where much more human-like abilities such as curiosity and ability to learn really quickly and planning and long horizon memory and planning and things like that mattered. And so people would be building these agents and then trying to evaluate them on existing benchmarks, and it just didn't show any improvement, partly because the benchmark didn't require any of these capabilities.
Right, and then they have to make a toy benchmark just to show that their network works, but it's like, why not give them a better toolkit so they can make a broader suite of tasks for these agents so that we can move that field forward?
That's why we wanted to open source it for people.
Well, one thing I've often wondered is, there's obviously when we think about how humans operate and the kinds of agents we'd like we'd love them to have this kind of advanced planning techniques and things like that. Although it can also be good to start really small with really simple examples. So I've often kind of wondered, it's like do we feel like we, for example, have a good model of how a really simple like nematode or something moves around in the world, or maybe even simpler things?
Yeah, so actually if you look at the tasks in Avalon, they go from simple to complex. And that was one of the things that we wanted to do. So the easiest task is you're already holding the food. There's a difficulty parameter. You're already holding the food, you can just eat it. And we find that actually this curriculum, without this curriculum, agents don't learn anything at all.
Yeah, none of the RL baselines work, basically.
Zero baselines work without the curriculum. That's actually pretty interesting.
It is, yeah. Well, and organisms do seem to have some behaviors that are built in.
Yeah.
So I was even kind of curious,
a lot of the algorithms actually that we use are a lot closer to a nematode or something that's really simple, where they have a sort of stimulus and action that's almost built in, almost not learned. The types of algorithms that we used as baselines in there, one of them is PPO, which is a really good algorithm, but it is entirely stateless. It just takes the input and maps straight to the action. So there's no thinking, there's no memory, there's no planning, and that works really, really well. So what that says is actually these tasks only require that. They don't require any memory, right? But some of them don't. Like some of them this doesn't work on. Sure. So it helps you separate which
ones.
Like
picking up a rock and throwing it at an animal does like not learn at all.
Yeah, you can't do that without any memory. Yeah.
Fascinating. I think that there's been this huge shift in recent years with the rise of the transformer that's really kind of shifted a lot of focus and what a lot of people a lot of people in this room maybe, or like startup people are all like, oh, like what's OpenAI doing? And even though like certainly when I think about what it's going to take to make AGI, my assumption is like a lot of reinforcement learning. How have transformers affected the world of reinforcement learning?
I think there's two ways. People use transformers right now as like a replacement for reinforcement learning with the notion of like decision transformers and like all the follow-up work from that, which is pretty interesting. But there was a paper at NeurIPS this past month showing that actually that's like a subset of the reinforcement learning problem. So it only works when your environments are not stochastic and one other criteria that I forget, but which was also important. And so they're not, you can't quite use them to replace reinforcement learning. It will seem to work if your environments are these like simple deterministic things, but they don't actually work in like the kinds of settings that we really care about. So it's not that you can totally replace it with transformers. They do a reasonably good job if you're in those simple settings. The other thing, and I think the place that's more exciting, is people using transformers as a model of the world or as a way of pulling information out of the world. That is much more powerful. I think that creates these really rich representations that the agent can have access to and can use to plan. Or you can use a large language model as like a planning agent inside, as like a component of a system. Like SayCam was an example of this from Stanford.
One of our podcast guests, Chelsea Finn, worked on SayCan, which is basically using large language models for planning for robotics.
And that seems to work reasonably well. So I think there's a lot of really cool applications. It's not a replacement for reinforcement learning. It's like a good component, a good thing to use in there for like understanding the world and for planning and for potentially other things as well.
Yeah, no, that's really exciting.
Yeah.
Okay, so I did want to actually ask you a little bit about science and funding, which are actually deeply related. So first, I mean, maybe just to start things off, just so people kind of have some sense, like how are you guys actually funded?
Yeah, we're funded by like independent, high net worth individuals who really want to see safe, intelligent agents in the world. And it's a very unusual style of funding. And they're very invested in kind of like long-term development.
Yeah, right. And so, so you've written actually about science funding, and you have this idea about meta science. How do you, well, first of all, do you want to maybe explain a little bit about that concept?
So 2 days before we launched the company, we also, my collaborator, Michael Nielsen, and I launched a meta science essay that we've been working on for 2 years. And the essay is about meta science as a way to drive change and improvement in the social processes of science. And the kind of framing that you might, a way to think about it is, let's imagine that we discover aliens, and these aliens are doing science. Now, if you think about these aliens doing science, like, do you think that they've discovered the atom? Like, well, it seems likely. Do you think that they've invented mathematics? It seems plausible. Maybe some really different set of representations than what we have, but like seems plausible. But do you think they have universities and PhD programs and advisors and tenure and the citation index and all of these other peer review? Maybe peer review, that's kind of interesting. But like how many of these social processes that we have in science today are truly fundamental? And so the essay really talks about, in part one, this idea that the design space for the social processes of science is way larger than we have explored. And we've explored this tiny, 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 tiny bit of it. And it proposes all sorts of potential ideas, but also, more importantly, we talk about kind of the generating functions for how might we find and discover latent potential in discovery space. And then the second half talks about why change is so hard and why decentralized change is actually really important.
Yeah, I mean, I feel like what you guys are doing and what you're building is, in a way, a thesis about, how could we fund research, right?
That's right. Yeah, this is like a meta-scientific experiment of like very strange, neither academic nor industry. We don't build product today because that would kind of focus us on technologies that are very, very too nascent to really be interesting. It's a little bit like Xerox PARC in the sense that like we're at the very beginning of this very important technology, and there are these important pieces to figure out. But it's also work that can't be done in academia.
Right.
So.
Yeah, so it seems like our society is missing out on this kind of work.
That's totally true. Yeah, it's kind of a one-off funding structure.
Right.
Yeah.
And do you have thoughts about how we could change that or enable more of it?
I have lots of thoughts on how we could change that.
Essay.
You could definitely read the essay.
Sure. But,
Maybe quick ones though.
yeah.
Yeah, I think one is like every funder says they want to fund high risk, high reward research, but in fact, like if you're in the right place, research actually might be very low risk if you have a certain type of information. To a researcher, like at a certain point, certain work feels very low risk to you, but it might feel very high risk to a funder. So that's one interesting insight. A second is there is this interesting relationship between like funders and the people they report to. So government funders, they are held accountable by politicians who are held accountable by the citizens. And the citizens, we want science to produce outcomes that better our lives. We don't want our taxpayer dollars to be funding all sorts of random stuff. And so this incentive structure causes this unfortunate kind of like narrowing of needing to fund science where you know it's going to succeed because you need to make that report to Congress in order to tell them that the NSF dollars are being well spent. And everyone here is very well intentioned, but the setup of the incentives as a system make it very difficult. Here, with high net worth individuals, one solution is more high net worth individuals funding things. I think that would be really interesting because in this case, the funder is actually the last stakeholder. They are the final stakeholder. And what we find is that actually lets us basically rethink things from first principles all the time. And it makes it much, much easier for us to do interesting work and like important work and continue to do important work even as things change in the field.
Yeah, that seems really powerful.
Yeah.
And there's actually I was curious about your take. I don't know if your organization is large enough for this, so tell me, but it's like, there's sort of like the macro funding problem. So how do we as a society, provide grants to researchers who will do the most impactful work? There's also kind of at the micro level, if you're running an organization, you have to figure out what to pursue and what to fund. How do you guys think about doing that?
Yeah. It's a really interesting question, and I think culturally we do lots and lots of things. As you can imagine, I think a lot about social processes. So the culture is very bottoms up. I think the thing I always tell people is like most companies, they're really proud of treating their employees as assets. But like asset, like this is like such a terribly low bar. Like it's an object that I own that provides value to me. Like, okay. And I really like to think about our team as team members as creative agents. Like every person, my job is to help them carve out a creative space that's really interesting and is like uniquely them and to unlock their superpowers and to basically enable agency. And so for us, a lot of the projects are very bottoms up. And on Monday planning, we basically say like, so what does everyone want to do this week? And then people will kind of like glom into different groups and just decide what to do. And so, yeah.
And since we've talked about it enough, and since we're still a relatively small team of 15 people, we still have a sense for high level the kinds of things we want to do. So it's not like people are going off in random directions and it's kind of people tugging against each other. It's instead like, well, we all talked about it and like this stuff seems pretty important. So I'll do this piece, you do that piece. Oh, okay, great. As opposed to like a kind of random hodgepodge of people doing their own thing.
Yeah. It's great to be well below Dunbar's number.
Yeah.
We've intentionally kept it not
Very
huge
small.
actually for a reason.
Yeah.
Oh, that's really great. Okay, so I wanted to have a section where we do underrated and overrated. So this is where I shout out a thing and you guys just tell me whether it's underrated or overrated and maybe possibly give one sentence for why. All right, let's start off with ChatGPT.
Overrated.
Probably overrated. It could be really good.
Sam Altman tweeted a while ago, this could have been done a few years ago. I think I agree with him.
Yeah.
Multi-agent reinforcement learning.
Probably properly rated, but slightly overrated. I think cultural knowledge is the construction of representations. We've done so much of that work ourselves already, as a culture. We don't need to learn it all from scratch. Yeah.
Okay, transformers for reinforcement learning.
In one sense overrated, in the other sense underrated. The overrated sense in literally using them for it, the underrated sense in using them as a component.
Causal machine learning.
Overrated.
Cicero, Facebook's diplomacy AI.
We're friends with Gnome, so...
Wait, but you should still say.
Well, I would say that it's a little overrated in that it's, the perception is like, oh wow, this like whole new thing. It's like a bunch of hacks, but I think in the long term it's underrated. Like the stuff that
I think
nobody's
it's actually
working on
really
is really
okay. I think it's really
interesting.
underrated because, but in a particular way, Noam has this idea of spending
You should.
spending compute at inference time is much more if we haven't spent very much compute at inference time, spending more compute at inference time is way more efficient than spending more compute at training time. And Cicero is an example of doing that. And so he's exploring a lot of ways to do that. I think the work is really interesting.
I see. Okay.
Yeah.
Wait, sorry. And how does that make it, or how is that played out in the way that they built that?
Yeah, I guess the longer story that shows an obvious example is he was playing poker. He was solving poker before, and in 2015, I think 2015-ish, the model obviously failed against humans. And the best way they were getting gains was by scaling the model. And so it was not deep learning, but it was a way of kind of like being able to represent more states in poker. And in this match, he was watching people, and he noticed that in the human case, if there was a really difficult hand, the human sat there for 5 minutes thinking about it. But the model just spit out an answer. And so this gave him this idea that, if we add more compute when you're deciding what to do, then maybe that actually makes a difference. And he found that every unit of compute spent at inference time was equivalent to 100,000 units of compute spent at training time.
Wow.
That's a huge gain, which is really interesting. So he evaluated this on some other later example and found a similar ratio also. So.
And it's analogous to how in chain of thought reasoning, the kind of idea is that, I just give the thing more tokens and it kind of thinks in tokens. So
exactly.
Chain
of thought is a really good example of kind of a very rudimentary early way of doing this.
Okay, language model embeddings.
It's rated depending on what problem you're working on.
Underrated.
Yeah. Some problems is not very useful. Other problems it is.
What's the problem where it's underrated?
I think people just don't use them for that much yet today, and I think we'll probably see them get used for a lot of stuff. So I would just say underrated. Yeah.
I mean, definitely as someone who worked on recommender systems in the past, it was very cool when I saw, I can just get embeddings. Like I don't have to train a big model.
Right.
Like I can just get them for free.
Right.
Did they work?
For the thing I was doing, they pretty much worked. But they're semantic embeddings aren't the thing that you really need for every single problem. And so, for example, search. Your query is semantically related to the target document, but it's not identical to the target document, or you wouldn't need to search, right? So, I think that search requires some nuance.
Yes, that's the problem with embeddings that are frozen.
Right. Yeah. Okay. Neural radiance fields.
Properly rated.
Properly rated. Yeah.
They seem cool.
Yeah. Exactly.
Internal family systems, the therapy technique.
Oh, deeply underrated. But also I think that people mostly do it wrong. Because it's not explained very well. There's not a good framework. I had this, we were just talking about, I had this idea of like trauma is overfitting and therapy is retraining, and like as a mechanism for memory reconsolidation, and IFS is kind of a good way to do that, but only if you add in a bunch of pieces. So somewhat rated,
AI is going to solve therapy also.
It'll solve some forms of talk therapy.
Group houses as a form of community.
Underrated.
Way underrated. Are you kidding me? Like, the story here is Josh and I started a house called The Archive in 2015. And lived in this big 25-person house, and that's where a lot of the genesis of this and other things came from. One of our housemates, Tom Brown, was the first author on GPT-3. Ben Mann, I think, was the second. And so, that was a huge transformative experience for me, at least. I think group houses greatly increase my sense of, for me, my sense of agency. I think people really become the average of the 5 people they spend the most time with. And so, like, picking those people is really important.
Have you read the Joseph Henrich work on like the weird people?
Oh, Secret of Our Success, or no?
Yeah, that's one of them, and then Weirdest People in the World is the other one.
No, I haven't read that one.
Well, The Secret of Our Success, I haven't read it, but it might say the same thing. It just basically says that like Western societies are really psychologically bizarre, and like one of the things that they're really weird at is that people are a lot less close to their families and more like trying to kind of like choose who they associate with. And so I always thought group houses were like the ultimate weird thing. It's just like take this to the ultimate extreme.
Yeah, I think there's this idea of scenius, like genius comes from your genes, scenius comes from your scene. And group houses are a great way of kind of beginning to instill scenius if you do it in the right way. And so you end up like going in this weirdness direction. I think generally intelligent is another good example of like weirdness. We've gone in this weird direction that's like a little bit different.
Yeah. Okay, Sutton and Bartow, the textbook.
Overrated. I was just looking at it on the way over here, just in case. 'Cause I wasn't sure when I was, yeah.
Textbooks are overrated.
There's some other really cool resources though. I would definitely, if you're really interested in RL, I would watch Sergey Levin's lectures.
Okay.
Those are really, really good. Yeah.
All right, great recommendation. Paperclip maximization, like the problem specification, is that a good way to think about things?
I think it gives you an interesting thought experiment, but it may not be how things play out.
That seems overrated. I think to our earlier points about safety, I think safety is a practical engineering problem, and those things come with a lot of nuance and complexity. And so I think a lot of these toy models for safety are a little bit misleading.
Yeah, and also lead to working on weird, like maybe not quite the right problems, but plausibly, it's good that some people are working on them.
Yeah. All right, how about fast takeoff?
As a
How
Well, as an
fast?
idea?
Well, I guess
How
that,
fast
maybe
is
that doesn't
fast?
quite go in the. Maybe that's not quite an overrated, underrated thing. But like, I guess like what?
What are our thoughts on
What are your
fast
thoughts on
takeoff?
that?
How fast do you define fast to be?
I guess I view fast as like. I mean, the relevance of speed of takeoff is that if takeoff is too fast, then humans might not be able to adjust in time, and that is how you get catastrophic outcomes. So I suppose too fast to adjust to.
I think it's going to be a lot faster than people expect anyway.
Yeah.
I don't think it's like you wake up and the world is different, but it doesn't need to be like that for it to be very transformative and kind of very disruptive.
It could be like over 2 years, the world is totally different,
Right, which is
and
still-
that can be very disruptive.
Yeah. Right. Okay, so you're more like 2 years, less like 3 weeks or something.
Yeah, I think 3 weeks is very hard.
I think the people thinking about the like 3 weeks or whatever, I think it's, in my experience, doing things in the real world, I've never done anything significant in 3 weeks, right? Like
Slows
it takes a
things
lot of,
down.
the real world has a lot of details. Like if you want to make a faster GPU, you have to make a whole new fab. This takes like a long time because you need to get all this stuff in the physical world, just so slow.
Yeah, and robotics won't happen for a long time.
Yeah.
Okay, so I did want to touch a little bit on how
You
you
had
guys.
one that you missed, language models.
Oh,
I think language
in
models are
general?
actually underrated in general.
Underrated.
Yeah, underrated.
Language models.
Language models, yeah.
Everywhere, like even like in this room, they're underrated.
Yeah,
yeah,
still underrated.
definitely in this room, underrated.
Okay. I'm working to adjust my. I rate them very highly. But I think of you guys as an amazing SPC success story. So what was your experience like at SPC, and how did that end up leading you to where you are now?
Well, we started a totally different company and learned it was an AI recruiter. And what we learned from that is that trust is the most important thing when working with AI systems, actually. That's what we learned through our customers is that people cannot work with black box systems where they don't understand how the system is working and what decisions the system is making on their behalf. And so that was actually an incredibly important lens to have on this problem and led to where we are now.
And how did SPC lead to you working on that?
I think we were
We
already
had
sort of,
decided to work on the problem.
we were
okay,
already
so
sort
you
of
came-
in the early
I see,
stages
yeah.
of that
Yeah.
before we started at SBC.
But it was just us at the time.
Yeah.
So it was
it
a
did
good
help
environment.
guide. It did help
Yeah.
like change the idea and everything.
Ruchi is a good friend. I worked with her at Dropbox.
Yeah.
And so we were in the first batch. It was a long time ago. And it was just like a small group of really interesting people who I just felt like there was a good community and we came here every day.
Yeah.
Nice. Yeah. I've greatly enjoyed it myself. Okay, so I guess let's turn it over to the audience. Are there any questions out there for our guests?
So a lot of people working on verification, especially formal verification, to see what are the mathematical bounds of the behavior of a lot of these agents. And it's getting into the nature of like how do these models work and how do they converge and all that jazz. There's so my question for you guys is that do you see that as a way to assess safety and interpretability, as some people think that's a good path to do? And if not, or if so, then do you think it's a near-term feasibility? Like it's like maybe in a year or two we'll come up with the grand unifying mathematical theory, or it's maybe something complex and it's a couple, like maybe a decade or several decades off?
I think there's two things that I would say on that. One, it's not like all tools are useful, right? Like formal verification is one level of tool, and it can help us say a certain type of thing about systems. If we look at like computer security, there are systems that you can make formal guarantees about and make them very, very secure, and that's actually really powerful and really great. However, we still have viruses and bugs, right? So it turns out that like it's not a full answer to all of our problems, but it's a valuable like tool in the toolkit. So I'd say I'm excited to see more people make more progress on that. It's not the thing that we necessarily work on, but like more things, more good. The other thing I'd say is that I am actually really excited for AI systems that themselves do the formal verification, because the formal verification itself is like so hard for people to do. That's the reason that we still have all these bugs and all these flaws and everything, because it's just so much work to do to formally verify a system of the level of complexity that we have for our real systems. But if we had AIs, if we had millions of AI formal verifiers, now maybe they could make our like higher level, more complicated systems actually secure and actually formally verified. So I think that is actually a pretty interesting thing, both for like formal verification and for like math proofs and stuff too.
Hey, I'm curious about your thoughts on roadmaps and roadblocks for agents to extract or augment just information and document retrieval.
Specifically document retrieval?
Yeah, or just information in general. I think that's like one roadblock we see when I'm a large language model. I don't know this.
Yeah, I think there's two things. One, there's techniques that people are doing now where you can break up the document into smaller pieces. So that's a way of getting there. And like we were just talking about embeddings, right? So you can take that and embed the like different pieces of the document and like kind of find which one was closest and like assemble a smaller context window that you can then pass to a language model to do a summary or something like that. So there are sort of hacks you can do today. There's also lots of research about how to do document summarization or how to get out particular facts or select particular pieces out of there. There's interesting work on retrieval for language models, like how do you retrieve out of a larger database.
Then you can just store the document in the database, and then there's a good retrieval mechanism.
And then there's also a good chance that over the next few years, we might see much, much larger context lengths than what are available today. Like right now, it's, because of the transformer architecture, it's sort of quadratic, and it's like, you can't make them that much bigger. But if people actually can move to linear attention or to something that's not quadratic, we might be able to see much, much bigger ones. And then that problem of like collapsing it into this context window might stop mattering as much. No guarantees on that, though.
In my experience, one of the big challenges with linear attention is that they perform worse than standard attention, and given access to unlimited compute, it's better to use non-approximating attention.
Yeah, but I'm saying there's been work as of actually very recently. There's an iClear paper, I think by Tri Dao. Maybe it's called like Hungry Hippos from like a few days ago that he posted about it. And it's pretty good. They didn't get rid of all the attention layers, but there's only like 2 attention layers and the rest are linear. And it works basically as well. They haven't gotten a chance to scale it up because it's like at Stanford, so.
So
yeah.
You guys are bullish on alternative architectures?
Not that necessarily bullish. I'm just saying that there's a chance that we'll get like something. I mean, in fact, that's already a good example. Like that could scale up and work.
Yeah.
So I wouldn't necessarily bet against all of the people in the community who are like working really hard on extending these context windows.
Curious about your general opinions on prompt engineering. Is this going to be an artifact? People are figuring out all these kind of crazy ways to get better outcomes with little cheat codes. What are your general thoughts on prompt engineering?
And it's really cool that people are able to get a way to think about what language models are today is they're like a mishmash of all representations of our culture. So like you can prompt them to get whatever representations out that you want. But also there's a spicy take that maybe prompt engineering is not a real job. It's just going to go away as we get better, more intelligent agents. And that seems plausible. Like I still do some prompt engineering of Vue, but not like super extensive, crazy prompt engineering.
Yeah, I do think that there'll always be a notion of like having to transfer context and tell our agents and systems what we want, right? And so that part is always going to be there. It might not look the same as today's prompt engineering, though.
Thanks. Hi. Why do you think language models are underrated? And then why do you think ChatGPT is overrated?
It seems like those two answers are in conflict, doesn't it? But they actually, yeah.
I don't think they are.
Yeah. So I think ChatGPT, I'm not saying that it's like super overrated. It's a really cool demo. I think it's cool that it's out there and it helped a lot of people see like how powerful these things are. I think the only reason I would say it's overrated is that, as Sam said, like we could have done this a long time ago if we really wanted to. It's not that, so the technology for this has been there. And actually the reason I would say that language models are underrated is the same reason. Like the stuff that we're going to see over the next year, like the things coming out in research, are going to make these systems even more powerful. Like if you think about it, ChatGPT was trained for the past year on the research that was done like the year before that. So there's a real lag in these systems, right? Because like it just takes time to get them together and get everything working and all of that. So it's not incorporating like a lot of new ideas that have come out over the past year, not to mention all the really cool stuff that's like in the research pipeline right now. When you really incorporate all of those, even if you did nothing else, language models are gonna be much more capable than they are today. So that's kind of what I'm saying. It's not necessarily language models of today are underrated, but like language models in general are just going to actually get a lot better than people expect.
Yeah, I think it's easy to look at them today and be like, well, they have all these problems. Like, they hallucinate and they have this issue where they can't detect burning hot coffee being okay. But it's like hard to think about what happens when an entire community of people try to work on a single set of problems and like solve them, and those problems are A, easy to iterate on, and B, very like valuable and clear if they're solved. And so I think just the feedback loop in this field is really, really fast, and it's hard to think about like conceptually how fast it actually is. But if you look back over the last 2 years, like maybe multiply by 3 or 4, and like that might be this year, and so that's one. Yeah, I guess maybe I won't say 2.
Yeah, so you mentioned language models being underrated. Do you think as models become better and better, there's more access for like more data from the OpenAI ChatGPT user interface? Do you think we're going to move to like one player having the like much better models than other players, and so it's going to be like harder and harder for like other players to compete with OpenAI or like let's say Anthropic or other players? Or do you think people will be able to catch up and like launch startups and still do stuff?
I think that my current expectation, although this is pretty weakly held, like I could see it going either way. My current guess is that it's probably more likely to go the commodification route of like it's that there are lots of different things that are almost exactly the same. Like as you mentioned, Anthropic, right? Like Anthropic has a really good language model. In many ways, it's like better than the GPT-3 one, but maybe GPT-4 will be slightly better. Certainly,
but worse
Amazon,
in other ways.
Right, but certainly Amazon and Google are working on their own systems. Google's probably working on 2 versions of this, like one at Brain and one at DeepMind.
Yeah,
right?
DeepMind's definitely got their own. They haven't released yet.
Right.
There are people working on open source ones, fair release, kind of an early version, but they're just going to get better.
Stability is definitely working on one. So I think that we'll see a lot more of them and all of them being kind of the same. Yeah.
Pass the mic around.
Yeah, so who do you think like will actually win out? Like what startups will do well? Will like the value accrue to the base model companies or like the foundation model companies or like the startups building on top?
I think everyone here is in a good position because I think if they do commodify, then that's great for everyone here, right? That means there's these really powerful capabilities that you can build on top of, and they're not going to capture very much of the value because it's a commodity. Like you can, just change off of one provider and change on to another provider instead as it becomes slightly cheaper or slightly better. So they have to really compete, but you instead get, like the people building on top of this, get to make more specialized things where you have like all these hacks that you made for your customers, or all this like customer specific data, or this like particular approach, or this particular design that people really like, or all these other types of things. Like if you made generally intelligent agents today, there are many things that just wouldn't change at all, because like structurally, there are like customers are already like, like LinkedIn wouldn't go away, right? Like it doesn't matter if you have a generally intelligent thing, like everyone else is already on LinkedIn, so you have to be on LinkedIn. It's like, fine, right? Like it doesn't matter how smart your company is. So there's these network effects that are really hard to displace. So you can build companies on top of these things that have network effects and that have other barriers and that are defensible. And since there's so much change, you have the opportunity to build all sorts of really cool stuff.
Yeah, historically, value has accrued to platform players in a changing environment like this. So, and platform is not the same as API.
Yeah.
Yeah, I wanted to ask about your thoughts on scaling. So, I feel like in reinforcement learning, scaling is at a much earlier point than it is for language models. And like, I mean, the largest like world models are like pretty tiny compared to the average sort of large language model. And so, and you know, and I feel like a lot of the approaches that are probably currently being tried in RL might need to change drastically in a much, at a much larger scale. I mean, the same approaches might not work. And then also kind of maybe tie that in with the difference between real world data and procedurally generated data, and then maybe for a final kicker, sort of how that relates to funding.
All right, I'll do the first one, and then I might have to come back for the other ones.
I can do the others.
Yeah, but for reinforcement learning, I think that's a good point. It's interesting that our current reinforcement learning algorithms, like you train them for longer with a lot more data, they don't necessarily get any better. Sometimes they get worse, like by a lot, which is pretty strange. But that isn't to say that reinforcement learning isn't useful at scale. So actually, ChatGPT, the main innovation, the main person behind it is John Schulman, who is the guy who made PPO, which is like the best, from our perspective, RL algorithm out there. And a lot of the contribution in ChatGPT they don't really change anything about the language model. It's much more on the reinforcement learning, on fine-tuning it, on like really adapting it for this use case. So I think reinforcement learning is really useful in combination with these other techniques and on top of these other models, not as we're going to take some RL algorithm that and then scale it up to be really competitive with these other models. It's more like a component. They're all just sort of like pieces of this.
Just like how transformers are not that useful for replacing reinforcement learning, reinforcement learning is not that useful for replacing a large language model.
Yeah, but reinforcement learning on top of transformers is like pretty useful. The second question was? Generated training data.
The difference between real-world data and procedurally generated data in the future.
Real-world data is great.
Yeah, use it as much as possible. I mean, one reason actually is that the real world is just much more diverse. And so when you have a lot more diversity and like a lot more edge cases, you have to figure out how to learn more general representations to deal with those.
Yeah, the reason that Avalon is generated is that it makes a controllable environment. So as scientists, we can understand like how do things vary with these factors of variation and like ask scientific questions. But if you want to make a practical thing for the real world, you're going to need to deal with real world data and all the edge cases that come with it.
Right.
Yeah.
I think you mentioned that robotics not going to happen in the. I think you mentioned that robotics not going to happen in the near future. Why so? Like, what are the main obstacles?
I guess I said that. And my estimate for things that can do a lot of digital tasks is much sooner than things that can do like general robotics. And the reason is because in robotics, hardware is really hard. There are two views on this. One view is held by some roboticists is, humans have eyes and we can do most things just with eyes. So if you add cameras everywhere on robots, you should be able to deal with the issues in robots. And if you have a human that's using a remote robotically controlled robot to do tasks in the world, the human does quite well. And so maybe all you need is eyes because that human doesn't get any feedback. And then the opposite view is, the issue with robotics, there are all sorts of issues with robotics. There are not enough sensors. You don't know how to fuse those sensors. There's the robot dies all the time. They're very expensive to make. So I think just because of all those things, even if the first is true, it just takes a long time for the field to move fast. And it's kind of like the opposite of what I was saying about language models, where it can move really fast.
Yeah, if you're interested in that, I would encourage you to check out the podcast that we did with Sergey. Well, we didn't do that one yet. We'll have a podcast with Sergey Levin.
Will be released in 2 weeks.
Pretty soon, and also the Chelsea Finn one, and there's maybe one or two other people that worked on robotics. So yeah, they have, everyone who works on robotics is like, ugh, this is gonna take forever.
So I think, one thing that was interesting that came up a few questions back was you talked about RL on top of GPT models, right? And then all these Instruct GPT models, ChatGPT, one of them, have have a transformer model with a human feedback RL on top of them. How far do you think are we from where we can substitute that human feedback out for a intelligent agent?
No, we've already done it.
Yeah.
Anthropic.
Yeah, it's the Anthropic's
had a
constitutional AI thing from a few weeks ago. It's a pretty cool approach that I think is definitely worth checking out if you're interested in that.
Yeah, instead of RL with human feedback, they do RL with AI feedback.
I'm curious, you have any opinion on the paper that Yang LeCun published last year around the path towards autonomous machine intelligence?
Yeah, I read it. I think it's interesting. There have been a few other people that have put out, they're like architectures for intelligence. I think they're really interesting thoughts, they're interesting ideas, good things to put out there. It turns out it's really hard to make such systems in practice, right? So we can't just like test it and see if it's real, but it's like a possible direction. So I'm glad that people are thinking about that stuff, but it's hard to tell, is that exactly the right way or not without sort of building it? And there's a lot of details that are kind of left as an exercise for the reader. So yeah, I think it's hard to say exactly whether that's the right way or whatever.
Yeah, I have a hot take, which is like almost any system, almost any system could maybe one day become generally intelligent, but some of them are just really hard to train. And so, as a human, I'm pretty self-learning. I die if I don't. And the nice thing about transformer models is that they're really easy to train, they're robust. So like such an architecture is a little bit hard to train. Might get there.
Hey, yeah, so I had a question. So there is a surprisingly large amount of online AI people, which we will call the less wrongers or the rationalists or the Eliza Yudowskis. I guess when they talk about AI safety, they're talking about existential risks, or we'll call it Skynet or the paperclip things. What's your opinion on this group of people? Are there controversies or fights between like the people who are focusing on more practical stuff versus ending the world, or what's your general opinion on that group?
I saw a really good essay by
Kelsey Piper?
Yes, that's right. Thank you, yes. Kelsey Piper at Vox about this, where she makes a good point that like in global warming, or for people that are working on climate change, it'd be really weird if there are some people that were like, trying to make solar panels, and there were other people that were trying to like get oil companies to like, be better in the environment, and they were like fighting each other. Right? It's like, well, we're like both working on different things that are like both trying to go in the same direction, right? Like, why are we fighting each other? I feel like you see that a little bit in the AI safety communities, and you have like safety and ethics versus this like longer term notion of safety. I'm hoping that as more people get in there and there's a broader set of views, that it'll become a little bit more like other fields where like people can kind of cooperate. Like, yes, you're working on the long-term version, we're working on the short-term version, there's people working on the medium-term version. There's a lot of issues to figure out, and it's fine if someone is like really interested in practical fairness and like applications of things today, they should work on that. If someone's really excited about making sure that we make safe systems and don't have more existential risks or aren't subject to those kind of problems in the further future, that also seems like a good thing to work on.
Just like the question about formal verification, like diversity in general is good. Most problems are going to solve a subset of the problem, the real world problem, because the real world problem is super complex.
I'm a biologist, so I'll preface this with that. Von Neumann wrote in the 40s about how it might not be possible to get a theoretical description of pattern vision, but only a machine that is capable of doing it. What if it turns out that there is no theoretical description of why neural networks work? Like, how does that affect you? How does that affect the field?
It's a good question. I think the answer is that it doesn't really affect it right now, because so much of our work is empirical across the machine learning field of like try stuff and see if it works, and the theory is a little bit lagging. I think for us, we're interested in the theory both because it will help with safety and robustness and understanding. So even if it doesn't help us build it, or if we don't have a perfect theory, but only more of a directional one, it still might be helpful for understanding. So I think that's our reason to pursue it still.
You can also, I think even in physics, we don't have a grand unified theory.
Right.
And so we don't need a grand unified theory of neural networks. That is not at all what we hope for. But instead, what we'd like to understand is what are the dynamics that are causing all of these things that we observe in the training, in the outcomes, in the data sets that we choose, et cetera. So those are, I think of it as like piecemeal theory is really what we're going for.
Yeah, there was actually a really cool paper last year, I think, maybe even the year before, about vision and like the sort of some ideas for like a theory behind like how motion tracking in particular works. I was like, oh, that's like pretty elegant and clean, and like, okay, so maybe we'll just develop them a little bit later.
Okay, so we're at time, and I don't even see hands, so I think we can conclude. Well, thank you so much, Justin and Kanjun. This was incredible. I learned a lot, and I hope you'll stick around a little bit.
Yeah. Thank you, John.
Yeah, thank you very much for hosting us.
Questions. You're so thoughtful.
I really appreciate that. Okay, thanks so much.
Cool. Thanks everyone.